All right, so those are our problems. We don't understand why the universe is big and why it has big things in it. Now, for 40 years, people thought of one approach to this problem, especially in the context of the Higgs, which is in this picture trying to find the analog of a pencil, of a hand to hold up the pencil, find a dynamical mechanism that would actually remove these violent space-time fluctuations that would of the sort that I drew here associated with the Higgs. And again, the problem of these fluctuations is a very structural one. So it stands to reason that a good solution to it would also have to be pretty structural. And we can go back to our menu of possibilities and see that there's one last possibility that was not used, which is to have elementary particles of spin 3/2. It turns out if you have massless elementary particles of spin 3/2, again, in some high energy approximation, that's only consistent if the universe has a certain doubling in it. Okay, and that's associated with the notion of supersymmetry. Now, one way of characterizing supersymmetric theories, it's a very convenient way of thinking about what's going on. It's not necessary, but it's a convenient way of thinking what's going on. Is that in addition to our ordinary dimensions of space, we also have some other dimensions, but these aren't kind of like boring extra dimensions that are just like some of our own that we curl up in some way. They're more interesting because the distances in these quantum dimensions are not measured by ordinary numbers. They're not measured by commuting numbers. I mean, if I have a distance in the x and the y directions, ordinarily, of course, dx times dy equals dy times dx. But the distance in these quantum dimensions anti-commute instead. So the product of the distances in the x and y directions, or any two directions, is negative, reversing the ordering. And so in particular, it means that the square of a distance in any given direction is equal to 0. Now, what that means is that I can imagine a particle moving around in our ordinary dimension, but let's say I'm trying to sort of doing a Taylor expansion of motion in the quantum dimension. Because of this feature that the distances squared are 0, the particle can't take more than one step in the quantum dimension. It can't take 17 steps. It can only take one step. When it takes its one step into the quantum dimension, it would be interpreted in the ordinary 4 dimensions as being a supersymmetric partner, the super partner of the ordinary particle. So we'd have an electron and we'd have a supersymmetric partner of it, where the electron takes its one step in the quantum dimension. Now, as I mentioned, this turns out to be a necessary structure if you want to have elementary particles of spin 3/2. But why does it solve this violent quantum fluctuation problem? The reason is, if we imagine going back to our picture of the box and making the box smaller and smaller, imagine at some point the box gets small enough that you actually see, you're able to excite things into the quantum dimension. Another thing I should have mentioned up here is that there's supposed to be a symmetry between the ordinary dimensions and the quantum dimensions. Well, as you make the box smaller and smaller, we have these more and more violent fluctuations, but at some point you see the quantum dimensions. There's supposed to be a symmetry between the quantum dimensions and the ordinary dimensions, but you can't have violent fluctuations in the quantum dimensions because you can't even take more than one step. You certainly can't go up and down and up and down and up and down. And so, since there's a symmetry between the quantum dimensions and the ordinary dimensions, that means that there can't be any violent fluctuations in the ordinary dimensions either. And so, technically, the presence of these doubled spectrum, these superpartners, cancels all the quantum fluctuations associated with the ordinary ones once you see them. Okay, so that was a paradigm for what was going on, is that we should find some mechanism to stabilize the Higgs, to remove these quantum fluctuations, and that notice that this made a prediction that you have to see whatever this mechanism is, whether it's supersymmetry or not, whatever this mechanism is, you have to see it at around the length scale associated with the Higgs, at around 10 to the minus 17 centimeters. If it only shows up at 10 to the minus 20 centimeters, then you still have the problem of something violently fluctuating massively more than it should, and it only gets stabilized at much, much shorter distances. So this made a prediction that not only that once we see the Higgs particle, we have to see other things coming along with it. The Higgs shouldn't be lonely. supersymmetry is a particularly dramatic example of other things that should come along with it, but the basic paradigm of finding some mechanism to stabilize these violent quantum fluctuations predicted that the Higgs should not be lonely. It should come along with lots of other particles that give you a mechanism to sort of stabilize it and explain why its mass is stable against these violent quantum mechanical fluctuations. And of course, famously, what's happened in particle physics over the past 10 years is we discovered the Higgs on July 4th, 2012, as I told you, and we haven't seen any other particles since, any other new elementary particles since. So that means that that this whole paradigm that something has got to remove these violent quantum mechanical fluctuations is essentially disproven. Now, it's not completely disproven, but I would say that if you turn into a pumpkin, if you're Cinderella and you turn into a pumpkin at midnight, it's 11:55. Okay, it's really very, very late for things to start showing up. Another indication that there is something wrong with this basic paradigm is that this basic paradigm also would make a prediction in the case of the cosmological constant. Remember, that was an even more violent problem, 10 to the minus 120. The problem with the Higgs is like a 30 order of magnitude problem. The problem with the cosmological constant is a 120 order of magnitude problem. But the length scale that's associated with the energy density of the vacuum, and I should have also mentioned that people wanted for many years, they had a sort of fantasy that this problem with the cosmological constant was so severe that some amazing mechanism would explain why it's exactly zero, right? We'll discover some incredible mechanisms someday that would tell us why it's exactly zero. And yet, when the astronomers discovered the universe is accelerating, the simplest explanation for the acceleration is that the cosmological constant is non-zero. And it is just around 10 to the minus 120. So we even have an indication that the size of the vacuum energy is not zero, but the length scale associated with it, it would be around a millimeter. Okay, so it's and we can all do the experiment to see if there's no new physics at a millimeter just by putting our fingers very close to each other and looking. So we have this very basic fundamental problem that quantum mechanics, and because of quantum mechanics in space-time, we expect more and more violent quantum fluctuations as we go to shorter and shorter distances. That should destroy all macroscopic order in the universe. And yet here we are, we have a nice huge universe with very weak gravity that allows large objects like you and me, the Earth, you and me, and so on to exist. Okay, so and this basic paradigm of some kind of mechanism to stabilize it, which already fails for the cosmological constant, appears to be failing also for the Higgs. So we don't know what to make of this. This is it's a big shock to many people, not everyone, but it was certainly not the sort of prevailing paradigm. And another point of view has emerged, which also involves a change in our notion of what space and time looks like in order to deal with these problems, but in a radically different way, which is to actually assume that maybe what we see in the world around us is not isn't what it looks like everywhere, and that if we zoom out from some sort of God's eye picture and look out at really enormous scales, we might see that our universe is actually a tiny part of a vast multiverse. Now, the idea here is that all of these regions in this bigger multiverse, they would have the same relativity in quantum mechanics, but they have a different menu of possibilities, okay? A different menu of particles, strengths of the interactions, maybe even the dimensionality of space could change from place to place. And this picture gained some support from developments in string theory in the 2000s, where there's an example of a theory that appears to be unique, one underlying theory, but the theory can have enormous space of solutions. And any given solution corresponds to a vacuum that would look like one menu of possibilities, but you can have lots and lots of them. And really, it's continuously infinitely many of them, but depending on what you condition on, let's say 10 to the 1,000, 10 to the 10,000, just gigantically a huge number of different possibilities. these huge numbers arise basically because of exponentiation. You have many choices you can make for how you curl up the extra dimensions, and the number of choices quickly grows exponentially in size. Now, if something like this was true, then you could imagine the following completely alternate explanation for why our vacuum energy is very small. You could wander around the universe, this multiverse, and look around and say, okay, here the vacuum energy is as huge as you thought, it's Planckian. But the world is curled up at the Planckian scales and it is doubling in size. It clearly is empty. Nothing is going on there. But even if the vacuum energy was like 10 billion times smaller than that, still the universe would be accelerating so tremendously rapidly that it would rip all the structure apart. In fact, if you look around, if you take our universe and you just imagine that the vacuum energy was only 5 or 10 times bigger than what we observe it to be, then even locally around us, the acceleration that would be caused by that vacuum energy would rip apart galaxies before they had a chance to form. So you can look around and say, look, in all these places, the energy, vacuum energy, here it has its natural value, here it's 100 times smaller. Why can I find one 100 times smaller? There's 10 to the 1,000 possibilities. Just statistically, there'll be one that's 100 times smaller, empty there, 1 billion times smaller, empty there, empty, 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 until you find these tiny regions where, by completely accidentally, but statistically possible, because there's 10 to the 1,000 different possibilities, there's a region where the energy density is 10 to the minus 120, which is also the only one where the universe is not empty. Okay, so this kind of reasoning is sometimes called anthropic reasoning. And this was a possible explanation for the smallness of the cosmological constant that was put forward by the great Steven Weinberg back in 1987. And it's the only scientific explanation that we have at the moment for the smallness of the cosmological constant. Maybe we'll come up with an explanation of this sort maybe we'll come up with another explanation someday, but it's definitely a possibility that's worth taking seriously. And this picture arises easily in a lot of pictures for deeper pictures for fundamental physics. The prerequisite that we have lots and lots of different possible vacuums we seem to get in string theory, and even though there is a natural mechanism for sort of populating all these different regions using the ideas of inflation in the early universe. So I think the picture both arises reasonably easily, and at the same time, there's something very peculiar about it. All these other vacua that are supposed to be out there, for like precisely the reason that our universe is accelerating, light from them can never make it to us, and so we can literally never see them. So we're using the existence of things outside our cosmological horizon that we can't even in principle see in order to explain something about a property of our universe. That's suspicious. It's not clearly wrong, it's not clearly right, but what I actually like about this entire way of thinking is that it exposes at the same time all of the conceptual mysteries about space-time and quantum mechanics. And I think there's a lot of reasons to take it seriously, but it's not a theory yet. It's only a cartoon for what might someday turn into a theory. But there's a lot of features of trying to make sense of this cartoon that are useful and force you into thinking about new lines of research about some of these questions. Okay.